Now I'll talk about the application, which is the website. The application is really basic. It uses basic JavaScript only, and there's only one style sheet. So I looked at the site on tablets. It's okay on tablets, but on the phone, it's not so good. But I only have one phone, so it's really basic JavaScript, but it's not that common because most most web pages I have seen are very complex. So I just briefly go over what I'm doing. So I use a simpler example, making recommendations at the bottom. So I'll talk about this part. In the HTML, that part is just one tag, and the JavaScript is generating all the stuff. So in the HTML, this is the recommendations page. In the HTML, it's just this. It's just one div tag with this ID. And then when the page is loaded, the JavaScript will, there's a JavaScript object that's attached to this tag. And then when the page loads, it runs get recommendations, and that's a function. And then when the APIs respond, this function will query the backend, which is Amazon AWS Lambda. And when Lambda responds, I'll render the results in movie grid and also models param table, which is this. This is a div tag. Div tag is the source of a param, this model params table, and models param table will render the results from the call. Well, if there's no result, it just renders nothing. So I'll go over the example of the recommend call. So in the documentation under app backend, there's a table of which page uses which API. So the recommend API is only for the recommendations page. So this is the recommendations page here. And I'll just refresh the page. So all my API calls are post. So here's the API call. The parameter of the API call is the user ID. So this application, there's only one user. That user is user ID -1. This is basically a hard-coded value. And it does support mobile users, but I don't have a sign-in page to simplify the project. And the tag ls is based on the choice here because tag ls. So if I ALS7, and there's another API call, that's ALS7. The algorithm parameter has changed to ALS7. So that's the request, and I'll take a look at the response. So the first movie should be like George Carlin Back in Town. So this is the first movie. The second movie in the response is Batman Assault on Arkham. So each response has a movie ID, a TMDB ID. So that's how the link gets rendered. When I click on it, it goes to TMDB /movie/242643, and there's a poster ID. That's where I get the picture. And rating is the user rating. So I have to go over here, to see. I rated Star Trek 2. I've been doing this all. Okay, so this one will have a rating. So that one from recommendation page doesn't have a rating. So param is Star Trek 2. That's the title. That's because I searched for it. And user ID is always -1. This time there's a rating. So rating's 4. The rating 4 matches here. Okay, and otherwise this structure, the title, movie ID, TMDB ID, and a poster, this structure is very common in this application. So that's a very quick overview of what's going on in the front end of the program. So I just went over, well, very briefly about the front end of the recommendation application. So before I go over about the back end, I want to go over app local. This allows you to run the application locally without using AWS, because it takes quite a bit of work to set this up on AWS. So to run it locally, you just start up the server program that I wrote and double click on the index.html page. So I'm in the app local directory. I hit that to start up the server. And you see it has started up with address and port number. I assume this port number is available. If it's not, you have to go into the code to change the port number. You also have to change the HTML page because it's hard-coded to use that port number. So hopefully that port number is available. So all the stuff is there. It's just like the real thing. I don't have enough reviews, so I don't think I have ALS 11C. And you can rate more movies. Well, not here. Star Wars. The Empire. Okay. So, Empire of Dreams. Okay. So you can rate movies. And as you do this stuff, you can see what's going on. Like I just hit rate, right? I just hit rate 4 stars, ID 1196. User ID is always -1, and operations add rating. So I just did that. So as you do stuff, you can check it out at the server program will print it out. Okay. And I'll just get rid of that. So that's how to run this locally. Because it takes so much work, this takes a whole bunch of work. So, okay, now I'll go on. Now I'll talk about the backend. This is the final topic of the presentation. The backend runs on AWS Lambda. It's really easy and it's really powerful. So Lambda is serverless. That means you don't run the server, Amazon runs the server. So you tell Amazon to run a function in response to events, such as when I click the rate, when I click on the star symbol to rate a movie 4 stars, Amazon will run a function in response to that AJAX request and then save something to the database. Lambda will scale automatically because Amazon's running the server. So if you're running the servers, you have to set up a load balancer followed by a autoscaler object. And you don't have to do that with Lambda. Amazon will do that for you. Lambda, because you don't have to run a server, Lambda will only charge you per use. So here are the prices. So when you make a request, Amazon will charge you a certain amount of money, and if no one's making a request, there's no charge. It's not like a server. If you have a server, at the very least, you have to run one server and an auto balancer, and there's some costs associated with that one server, even if nobody comes to visit your website. So Lambda can scale down all the way to 0. That's what this is. Lambda is quite fast because of Lambda at Edge. Lambda at Edge means that Amazon is capable of running Lambda on the CloudFront computers. So Amazon is capable of running Lambda on these computers. So if you start your own server and your server is in, say, over here in the Oregon data center, it's going to be slow for people in other parts of the world. But if you use Lambda, and if you're using a database that's close to Lambda, it could be a lot faster. Lambda has a 100 millisecond minimum price. So that means Lambda cost for Python can be as low as, say, for other languages, say Java. So traditionally, web applications in Java, because Java will run much faster than Python. Okay, but if you're on Lambda and if you keep it under 100 milliseconds, it doesn't matter. Amazon will charge you this price whether you're using Java or whether you're using Python. So Lambda narrows the gap between Java and Python in terms of execution efficiency, because of the pricing model has a minimum number 100 milliseconds. With Lambda, one complexity is that you have to specify the memory. You have to benchmark each API and specify the memory explicitly. So look at this. So some APIs are 128 meg. This API, the similar, this is when the user click on the similar movie link, and the API looks for similar movies. This one's 256 meg. And recommendation and search takes the most memory. The recommendation is using 512 meg. This is something I set up. This is not something that's automatically figured out currently. So that's one complexity of Lambda. Basically, when I set up this function, there's a slider down here, and I have to slide it, to 512 meg. I can go up to 3 gig, or the minimum is 128. So get it here, 512 meg. Oh, I have a table. I have a benchmark table. Where's my table? Okay, there. Here's the table. So Lambda memory usage. So when you run Lambda, there's a log in CloudWatch, and in the AWS log inside of CloudWatch, they're going to, or is it CloudTrail, whatever. So in the log file, they're going to tell you how many memory your Lambda script took. So I got these. That's where I got my numbers. Yeah, recommend is by far the biggest one. Recommend it's not easy to say exactly what's the maximum memory requirement. Recommend has many global variables which are loaded only as needed. Basically, you see this. That's the recommendation page, and it has a lot of recommendation engines. So depending on which engine gets used, different engines use different global variables. So I try to maximize the memory usage by cycling through all the recommendation engines, which should load all the memory variables, should load all the global variables. So, but I'm not totally sure. So I'm not totally sure this is the maximum memory usage, but should be. So that's my overview of Lambda. Just be sure to set the memories individually. And my application storing data inside DynamoDB. DynamoDB is, it's DB is not, despite the letters D and B. I want to highlight D and B. Okay. Despite the letters D and B, it's not necessary. It's not really a traditional database. It's more like a lookup table. So the layout looks like this. So in a traditional data table, you will have one row per user. The first row will be the first column will be user ID, and second column, third column, fourth column, and fifth column. So these all be columns, but in DynamoDB, the first column is user ID, partition key. That means I look it up by equality. And then the additional columns are bundled together as rows. That's just how it works out better that way on DynamoDB. So this column is stored as a row, but it's, you think of it as a column. This column, tag count parameter, that's the parameters. That's the stuff when you use tag count. That's this stuff, these numbers. And there's more columns than that. I'm just saying that for tag count, but you also have ALS underscore params, you have tag ls underscore params, and so on. Did I say that? Oh well. Oh, I'll just show the table. I'll just show the table. Okay, so there's, for each recommendation engine, there's actually an underscore params column, but it stores a row. Yeah, so even though I say only one, but I meant there's multiple. Same thing here. Underscore rec stores the means recommendations, and of course there's a underscore rec for every single recommendation engine. Ratings store the user ratings, but it's in binary form. Not going to be able to see anything here. So for the params, you can actually see it's actually in string. So you can actually see some of this. So tag count param 0.558 copy. This might actually be here. Yeah, so 0.558. Here you can be seen from the database because it's in text, but a lot of this data is in binary, so you have to use code to see what's there. You can't just see it. You can't just see it by looking at the AWS control console. Status, this column contains a lot of timestamps. So whenever I do something, say I make a rating, say I rate a movie, that triggers a timestamp. Or if I remove a rating, that also triggers that also puts in a new timestamp. I don't generate the recommendations immediately, so I generate the recommendations lazily. So the recommendations have a timestamp, right? Say tag count has a timestamp, and ratings has a timestamp whenever I rate something or if I remove rating. So when I come here to the recommendation page, the code is comparing those timestamps to see do I need to generate recommendations. So that's what the timestamps are. So I briefly went over Dynamo, how I'm using DynamoDB, and briefly went over the timestamp mechanism. And now I'll talk about the build process. How do you set this all up? I actually have a build script for this because it's not that trivial. So Lambda, most of my Lambda is here, okay. So most of my Lambda is, it's not that simple. It's too large to enable editing, so there's nothing here you can upload a zip file. That's it. I think there's one where I can edit directly. I think maybe this one's the only one. Yeah, rate. So this one's the only one where it's simple enough to just, edit this like inside of the web browser, because it only has 2 files. But all these other ones have a lot of binary files, all those variables, .bin files that I've been talking about, such as, similar movies.bin. So most of these Lambda files cannot be viewed directly inside AWS console. So Lambda for small files, like for small projects like this one, you can go in here and just edit that. You can add a new file here if you want. But for anything larger than some really basic file, you have to send them a zip file. And my upload speed is pretty slow. So I have a little picture here. So here's my computer. If I were to upload directly to Lambda and let's say it's a zip file, and most of these zip files are like, okay, let's say this is the worst one. Let's say I change like one little character in a comment. I still have to upload all 57 megabytes of zip file if I were to deploy directly. And there's another reason why I can't deploy directly. But one reason is that even if I make a little tiny change, I have to re-upload the whole zip file, and my upload speed is slow. So that's one reason. So the build script, what I'm doing is I'm uploading the changes to S3, but I'm only uploading changes. And then I'm building a zip file on EC2. And then I'm uploading the zip file to S3. And then I take from S3 to Lambda. So in Lambda, say recommend, let's say that I made a change, I can get a file from S3. Okay, and that will be much faster. It's much faster because I'm only uploading the change to S3. And then S3, Lambda, EC2, they're all in the same data center. They're all in the same building, so communication between them is very fast. So that's what the build script is trying to accomplish. One thing, the first thing is to upload only changes to S3 so that I can do my zip file, I can do the upload within Amazon Web Services, so to deploy files quickly to Lambda, because my upload speed is slow. Okay, the other thing is that Lambda is Linux, and this particular one, the really big one, the 57 megabyte one, well, it's that large because it's using NumPy and SciPy, and both NumPy and SciPy are not pure Python libraries. They have parts written in C++. So that C++ stuff needs to be built on Linux. Okay, so Lambda is the Lambda runtime is very basic in that the Lambda runtime for Python 3.7, it's gonna have the Python as standard library, and it's gonna have the Boto3 library, which is Amazon's library. And that's it. It does not have NumPy, it does not have SciPy. So NumPy and SciPy has to be built into the project. And that has to be done on Linux because it has to match the Linux environment of AWS Lambda. So that's the other purpose, is I'm uploading source files, but the NumPy and the SciPy is built right here and then uploaded to S3. So I'll kind of demonstrate, I'll go through the build steps. I'll go through the build process. So it starts on Windows because I'm developing on Windows. I'm just deploying on Linux, copying the ALS models manually. So the ALS models refer to these files, the item factors and the movie IDs, those bin files. As mentioned as explained when I talk about the slide, those are the files trained using 100% of the data. And I don't have a special naming convention for those files, so those files need to be manually copied to the application directory and to the app local. So that's the first step, copy. There's no command because I just drag and drop, or I don't know, Control C. So recommend. So you can see it has all the files here. The ALS model files trained using the full data set. So locally in Windows, run python.build. This is inside the app directory. I should say yeah, it's python_app. So this is inside the python/app directory here. So I just ran it actually. And it's the first time we run it, there's gonna be more stuff than this. So because I've been running my own scripts, so the bin files are updated. So my build script will detect what files have changed and will upload these files to S3. They did not really change because these aren't really new files. I'm just doing stuff for the presentation. So this part, okay, python.build.py represents this part in this 3-step process, uploading files to S3. More specifically, uploads the files that has changed to S3. So it gets into this stuff. So this is like a direct mirror of this stuff. So the array, recommend, search, similar. So you see the array, recommend, search, similar. There's a shared, because there's some files that are common to multiple projects that's in here. So yeah, there's a bunch of files like this. Some Python files, a lot of binary files are shared, are used by multiple APIs. So they're stuck in share. But over here, I'm just manually, there's no shared folder here. There's no underscore shared folder here. I just have multiple copies. And the build script takes care of that. The build script actually makes sure that they're the same. I'll talk about shared files a little bit later when I go through the process. Okay, so copying the ALS model, python.build.py that uploads to the S3. So the next step is on Linux. So Linux, I have started an all new directory that has nothing in it, but you need those 2 files, right? This is the build script, and this file contains information about what's in the project. Okay, so when running it on Windows, I need the build script and the project file. So build.py is for local. EC2 underscore build.py is for EC2. So EC2 underscore build.py does this stuff, does step 2 and 3, which is downloading from S3, but only downloading things that have changed and uploading the zip file to S3. And it does the zip file here. So I'll run that. Wait. Well, I'll run this first and I'll talk about this stuff. This is the building the NumPy and SciPy. So this is totally new, right? The folder, the temp folder is completely blank. So I have to download everything. Okay, so recap. This is a completely empty folder that has like nothing in it. Well, it's got this. I got rid of that too. So it's a complete, okay, so at one point I removed some stuff. So at one point when I typed in the script, it has a build.py and it has a project files.py. So there's nothing else in it. So I'm downloading all the stuff from S3, And then I'm doing the zip file. I'm doing the zip process. See if I can see the zip command. So yeah. Okay, so the zip command is not being printed, but the zip command itself is not being printed, but as the zip command is happening, it's printing, it's adding it to a zip file. And then the zip file goes to S3. And at the very end, there's a summary that, I have done these zip files to S3. So S3 now has these files there. And so if I want to say update to recommend, I would copy this line. I would go over here, S3. So just paste your link right here. See if I can show the zip file here. So it's okay. Now there's like directories representing the Lambda functions I'm trying to build. So it's in the recommend. That one's the biggest one. I haven't done the NumPy and SciPy yet. That's what I'm saying. So maybe what's the zip file? Okay, so ls. Okay. So that's the zip file, but it's actually not done yet. This isn't enough, right? There's no NumPy and SciPy. Like I said, this function, this code for recommendation engine, it needs to use NumPy and SciPy, and those libraries are not present in the Lambda runtime. Go back here. And so the files, that's why it's so much bigger than all these other files. That's because of NumPy and SciPy. So cd recommend, going to the recommend directory, have to run this command. So what that command does is install NumPy into the local directory, and I also have to install SciPy. So now there's a bunch more stuff, right? There's the stuff from before that, and it's got NumPy and it's got SciPy in it. And so, in the code, it says import NumPy. Okay, so it knows where to find it now because Lambda doesn't have it. And import SciPy will just dive into that directory and grab the stuff over from that. So now it's ready for upload. Okay. Well, it's no change because that's a problem. It didn't detect any change on S3 because the changes were made locally. Oh well. So the workaround, well, how does it know, right? Well, it knows because of the meta file. This meta file, it's like a Python dictionary that has all the timestamps on it, because the timestamps here are not that reliable. Because the timestamp on EC2 is different from timestamp on S3. S3 timestamp is like a metadata. So anyways, just remove the meta file, and then it doesn't know the real timestamp. Now it's doing all this stuff again because it doesn't know whether things are obsolete or not. Now you can see this huge bunch of NumPy and SciPy stuff being added to the zip archive. So here we go. So this one now has the NumPy and SciPy within it, and now it will work if I upload to Lambda. So that's me going through the build process. You have to copy in the ALS models manually, build on Windows, and that will upload to S3. Uploads S3 here. Run Linux commands. Yeah, you have to install NumPy and SciPy manually because these are not present in the Lambda runtime. And then run this script, which will upload to, well, it downloads from S3, builds a zip file, and then uploads it back into S3. And then finally in Lambda, you can go to any function, and then, well, even if it says code in line, you can always, upload the file from S3, put in the link here, and hit save over here, and that's how you build the Lambda functions. Now I'll go over the project files. I'll go over the scripts. So locally, there's a project file and there's a build script, and there's another one. This one's for use on EC2 build script. So the key is a project file. The project file is a list of files. So here's a project and uses these files. Okay, so the big one is the recommend. It has a lot of files. All right. And some files are expected to be just there locally, like models.py. The expectation is that the models.py is just here. Okay, it's like a local file. Okay, and some files are pulled in from somewhere else. So I call these upstream files. So this file generally counts.bin. This file comes from the full data project. So for this to work, you have to follow the same hierarchy that I'm following. This is an app folder, recommend. So app/recommend. And there's full data. So Python/full data. So full data is on the same level as app. So it's going to the parent directory, going to full data, it's pulling in. So that's the path. So this is the file name, this is the path, and so on. Upstream files are files will be copied from that upstream location as needed. And by as needed, I mean I look at the file modify time. So if this version, okay, this is in, which one is this? Oh, it's in recommend. Oh, they're all in recommend, I guess. Okay, so if this version in full data /data/in, if this version under full data is newer than the version in recommend, it gets overwritten, and that's what happened, right? Because so it matches, right? This is so that's what upstream means. But the local file is allowed to be later. So if the local version is newer than the upstream version, nothing happens. So, and then there's shared files. So these files are utilized in multiple projects, because I'm taking the microservice kind of approach here. So this is the back end. Now you can have a single Lambda function that's really complicated and it does all 5 things. So, but you have only one single Lambda function. Okay. The alternative is to have more Lambda functions and they do less things. So individually, these Lambda functions are easier to understand than a single monolithic function, but there's more duplications. That's the downside. So this file is utilized by multiple Lambda functions. This is the DynamoDB accessing. This access DynamoDB. So all the functions that access DynamoDB will use this file. So okay, so this file is shared in 4 places, just about everywhere, almost everywhere, but not here. So share in this, and this. And the idea is that if I update any one of them, all of them will get updated. So that's what share file means. It's going to look into all 4 of them and find the one that has the newest modified date and just copy that to all the other ones. So I'll demonstrate that. I'll actually modify it, and so I have it here brought up. Recommend movie data.py. I'll modify, and then everywhere it should update. So I'll modify S. That doesn't do anything. That's a comment. I'll just change it back, even if it's a comment. Okay. So I modify that file, and when I hit python build.py, it's gonna update that. Okay. So it saw the movie data.py got updated, and then it's updated this one, updated this one, updated this one, but not recommend one, right? Not app.recommend, because that's already the latest one. So it updated the movie data.py in the other functions, and it uploaded that to S3 at _shared. So I'll go to this one now. This is the EC2 build. So this one saw that, and it's gonna do that NumPy and SciPy zip thing again. So, and I think I lost it. But in the very beginning, it saw that. It saw the update in. Let's see if I can go back. Just too many. Yeah, there's too much stuff here. So in the very beginning, it saw that, and it changed that, and then it detected the change because I changed the recommend. So I should change something else, because if I change the recommend, it's gonna build the NumPy and SciPy archives, and then I can't see the output anymore. Okay. So I'll change, say, oh, but this one's also, I'll change this one, rate.py. So save, okay. So rate.py is now changed. So rate.py has been uploaded as 3. All right, it detected the change and all modification have been uploaded as 3. And then okay, now this is better. It's not doing the NumPy and SciPy archiving. So no change for this project. For the rate project, it saw rate.py got changed, and so rate.py got built. And in the final conclusion, this is the only one that changed. And just copy this address and go to Lambda, and then put this address in there to update Lambda. So I gone over the project, the build process. Briefly, I've gone over the project files. It's a bunch of files. It's a dictionary of files. I gone over the upstream file mechanism, and I demonstrated the share file mechanism. I demonstrated that the build scripts here, they will detect changes and then update only the changes. So that's it. That's what I want to say about the build process for now. And this is the end of the presentation, so I'm done. Okay, finally.